Hey guys, welcome back to Determining the Electric Field for a Disk of Charge Part 2. In this video, once we set up the integral that we're actually going to solve, we're now going to do the integration that is established. Okay, well first of all, this integration is a little tricky because we have multiple things going on here. First of all, our variable that we're integrating, our independent variable r, is not only squared on the inside of this, it's also inside this other function, and it's also multiplied by this linear function r. So there's a lot of things going on here, and you can see that you would need to do something to get it to the place that it needs to go. My first step whenever I'm looking at something that's a little bit more complicated is to look at U substitution first before I look at anything else like integration by parts. And so that's what I'm going to start with, because sometimes it will factor things out that actually make it easier to solve. So the U substitution that I'm going to use is I'm going to set U equal to R squared plus Z squared. Now the reason I'm going to do that is I know that one of the easiest integrations that I know of is if I'm integrating x to the n, the solution to that would become x to the n plus 1 over n plus 1. Well, similarly, I can also integrate x plus a to the n, and it will do the same thing with a being some constant, not all of this. So it's going to be x plus a to the n plus 1 over n plus 1. So essentially what I'm saying is, if I can make this u to the negative 3 halves, doing the integration of u to the negative 3 halves is pretty easy. That I can handle. Now, I still have this r out front here, and I can't just integrate u to the negative 3 halves times r, because that's not going to be the same thing. So I'm going to first do this u substitution step and see if I can simplify out this r. Okay, so the procedure for U substitution, I have what my U value is. Now I'm going to take the derivative of U with respect to R, and that's going to give me 2R. So now when I'm going back to my original equation here to make some substitutions, I can already see that the R that's over here is going to be able to do something with this R, and I have a 2 over here that will be able to assist as well. So let's get this in a form that we can use. So dr is going to be equal to du over 2r. That's going to be able to be put back in here, and then of course my u. So let me rewrite now my integration, and again remember I'm just putting a as all of this so I don't have to keep writing it out. So I'm going to put a times 0 to r, have this little r here, and now I'm going to put in my u to the negative 3 halves, and instead of dr I'm going to put du over 2r. I'm just going to move the 2r over here. Okay, so far so good. I still have this 2 over here, but I know there's a 2 in my a substitution here that will factor out, so I can pull that 2 back in. So what I'll do now is just say that a is equal to kz sigma pi, and the 2's back in here. Okay, so I can factor that out. This makes this a lot easier. So I've got all of the constants times integral from 0 to r of u to the negative 3 halves du. Now that's a very manageable integration to do. The fanciness of doing u substitutions and being able to see when things will cancel out just comes with practice and time and experience, and you'll get that eventually. Okay, at this point, my integral, I have a, and I'm going to actually do the integration here. So u to the negative 3 halves plus 1, so plus 2 halves, is going to give me u to the negative 1 half over negative 1 half, which complex fraction resolved would be negative 2. So negative 2 u to the negative 1 half, and that's going to be evaluated from 0 to r. Now I know that the r doesn't make any sense here, but I'm about to substitute back in the u that I originally had. So I'm going to put here a times negative 2 times r squared plus z squared to the negative 1 half, evaluated from 0 to big R. Okay, at this point I'm ready to do my evaluate this at the limits. And so let's go ahead and set that up. So I'm going to move this all the way up here. So I have a times -2, all right, times, let's get going on this one, r squared is now becoming big R squared because it's substituting in, plus z squared to the -1/2 minus 0 squared plus c squared to the -1/2. Now let's substitute or simplify this out just a little bit. So the first thing that I will do here is put my a value back in. So I have k times z sigma pi. Okay, and then I have the -2 over there, so I'll just pull that all the way out front here. And I'm going to have this first term, which is r squared plus z squared to the -1/2 minus z squared to the -1/2. Okay. At this point, I'm going to do something that you may not notice, but I know where I'm going with this, so this is why I'm going to multiply or distribute this c back in here, okay, and I'm going to be left with -2k sigma pi, okay, and now I'm going to rewrite this slightly, so I'm going to have z here in the numerator, because this, remember, is on the denominator, and that's going to be r squared plus z squared to the 1/2 minus z over z squared to the 1/2, which is just z. Those can cancel out, and so I have this expression at this point. Now what I'm going to do is, because I know that z over z is just 1, and I would have z over r squared plus z squared to the 1/2 minus 1, but I have this negative in here, and I'm going to go ahead and multiply it in, so that what I would end up with is 2k sigma pi times 1 minus z over r squared plus z squared to the 1/2. And there I have an expression for the disk, which is a little cumbersome, but it still actually does make a lot of sense. And if you look at what's happening here, as z goes to being very large compared to the radius of the disk, this all will just go down to r squared, and I would have 2k sigma pi over r squared. And I could actually do some other simplifications here if I get rid of this k, which is going to leave me with an expression that's basically just kq over r squared. So in essence, what you can think about is, when you're finding the electric field at some point away from a dot, we're just using the original electric field equation. When it turns into a ring, if you're close enough, you have to use a special equation. But if you move really far away out here, then the ring basically just looks like a dot again, and it's not going to have its own special equation. It's going to go back to being the E equals KQR over R squared equation. Same thing happens here. If I had a disk, if I'm close enough, I have to do a different expression, this long thing over here. But if I move really far away, the disk is basically just a dot. And so this equation is only when I'm close enough to where z is closer to the value of r rather than when it's really far away. Now, I encourage you to try to put sigma back in here as q over 2 pi or pi r squared. Factor out the pi's, and you can simplify this down a little bit more, and you can see a little bit more of what it looks like. Remember, k is also 1 over 4 pi epsilon naught, so that can change this expression as well. But I hope that helps, and you can think about how going the next step along that conceptual map that I had previously right over here, you can see that the next step could actually be finding for a sphere of charge, which could be done as well.